Okay, let's talk about significant figures and how significant figures can tell us precision of an instrument. And typically, when an instrument is precise, it's also accurate. Okay, so I want you to look at this example here. We have zoomed in on two rulers. Okay, so these are both centimeter rulers, and the top one has 10 calibration marks in between the centimeters, but the bottom one doesn't have any calibration marks between the centimeters. Okay, so when I look at this, I know that this measurement, that the whole number I'm going to be certain of, and I know that the 10th number I will be certain of, because I'll be certain that I'm past calibration marks here. And then I'm going to make an estimation in between calibration marks, and that's my uncertain value. Now, for the one below, I am certain of my whole number here, but I don't have any calibration marks in between the whole numbers, and so I'm going to make an estimation between this. So that's going to be, the 10th place is going to be my uncertain value. Now let me show you an example where students struggle with this the most. So we have an object that started all the way back at 0, and now we're measuring it, and it's gone to 8 centimeters. Okay, so we are certain that it's past 8, and we are certain that it's past 8.1, 8.2, 8.3, 8.4, and it is right at 8.5, and we are certain that it has hit that calibration mark. Now, we've determined and looked at this and we said, you know, that's right at that calibration mark. I'm certain it's at that calibration mark, but I still have to make this estimated number here. Because the scale of this, the precision of this instrument, allows me to make an estimation in between. And I estimate that this object is 0.1 of the way to the next calibration mark. Now for the same object down here, I am certain that it's past the calibration mark of 8, and now I'm going to make an estimation in between, and it looks like it's exactly halfway, so I'm going to say that's 0.5 of the way, and that's my estimation. Now, even though these numbers are the same, they hold different meaning. We know that this value is far more precise than this value. And usually with precision comes accuracy. That this is a more accurate answer of the length of this object than this is. Because there's a whole component here that we couldn't estimate because we didn't have the calibration marks to make that estimation. So this could be anywhere from 5.1 to 5.9, but here we know that this is 5.50 and then a value after that we couldn't accurately tell, right? So more precision, more accuracy. Less precision, less accuracy. If a value is measured right on a calibration mark, you're certain of that calibration mark, and then you'll want to estimate that you're 0.1 of the way to the next one. Okay, rules for significant figures. We've talked about how to use and find significant figures in measurements, but now we need to talk about significant figures in calculations. Okay, so there are some rules for knowing how many significant figures a number, a measurement is giving us if we don't have the tool. If they said, okay, here is my value and then you can determine sig figs from that. Okay, so the rules are, if you have any leading number or leading zeros, any zeros before whole numbers start, then those zeros are never counted as significant. Okay, so if I look at this, my numbers between 1 and 9, they are always significant. So these don't count, but then I have 1, 2, 3, 4 sig figs in this example. Oh, sig figs. Trapped zeros, zeros that are in between whole numbers, those are always significant. And it doesn't matter that we have 2 in a row. It's the fact that we have a whole number here and we have a whole number there. Okay, numbers between 1 and 9. So this one would be 1, 2, 3, 4, 5 sig figs. Trailing zeros are where it gets a little confusing, so pay close attention. Trailing zeros are significant if there's a decimal place. If there's not a decimal place, then trailing zeros are not significant. And it's not just the zeros after the decimal place. If there are trailing zeros, whether they're before the decimal place or not, but the number does contain that decimal place, then all those zeros are significant. So this value has 1, 2, 3, 4 sig figs. Okay. This one, same idea. All those are significant because of the decimal place. So we have 3, 4, 5 sig figs. Now this trailing zero is significant because of the decimal place. So the 5 is significant and this 0 is significant. So we have 2 sig figs. Here, these trailing zeros are not significant because there's no decimal place. So the only digit there that is significant is the 5. And so we have 1 sig fig. Okay. Now, I know that zeros can get tricky. And I want us to look at this and again make some predictions. So how many significant digits do we have in 1,000 kilometers? Well, in this example, there's no decimal place. These trailing zeros are not significant because there's no decimal place. So we have 1 sig fig. So our measuring device only had calibration marks of thousands. Okay, there was no values in between the 1,000 calibration marks. So that's not precise at all. I mean, there's huge room for error in between there. Here we have our decimal place. And so this would be 1, 2, 3, 4 sig figs. So we had calibration marks for all of those values, and then the last one was the estimated value that they measured. And so this was far more precise. It contained a lot more calibration marks. Now, numbers in scientific notation. Here's how it works for looking at sig figs. The times 10 to the power is never significant. And then we apply the same rules to the coefficient. So here, because there is a decimal place, the trailing zeros are significant. So we have 1, 2, 3, 4 sig figs. All right. Hit pause. Run through these on your own. And then come back and play it through and see how you've done. All right? Okay. So these are all digits between 1 and 9, so every single one of those are significant. So we have 3 sig figs. And rule number 1 tells us all non-zero values are significant. 6.2, the 6 and the 2 are significant. The 0 is significant because of the decimal place. So we have 3 sig figs again. And for this one, it's rule number 2, but it's the last part about trailing zeros. In this situation, all trailing zeros are significant. These ones happen to be to the right of the decimal place. Here, the 6 and the 5 are significant. The 0 is significant because it's trapped in between those non-zero values. So we have 3 sig figs again, because all trapped zeros are significant. Leading zeros are never significant. It doesn't matter which side of the decimal place they're on. If it's leading zeros, not significant. So we have 1, 2, 3 sig figs. And this goes with rule 2, part A. And so leading zeros are not significant. We have a trailing 0, but there's no decimal place, so it's not significant. So we have 1, 2, 3 sig figs in this value. Okay? And for this case, our trailing 0 is not significant. All right, determine the number of sig figs for each measurement. I want you to try this one on your own, okay? And then come back and see how you did. So go ahead, hit pause, give that a go. Okay, here I'm just going to give you the answers. If you have any questions, please contact me, send me an email, or come visit me during those study session times. There's our number of sig figs. Right, now rounding numbers and calculations with sig figs is going to be our next part of and last part of this videos for today. We're going to end with some rules that we have to follow when we're doing calculations with our sig figs. Okay, so take a breather, come back, and we're going to finish up this set of notes.